Good afternoon, and welcome to the 8th in the series of seminars looking at our future in space. My name is Cordova. I'm NASA's chief scientist, and I have the pleasure of introducing today's speakers. But first, I want to ask you to mark your calendars for January 29th, same room, same time. That will be to this year's Administrators Series as the Super Bowl is to football. It'll be a wrap-up of what we've learned and a plan for the future. Where is NASA science headed? Mr. Goldin himself will give that talk after a short video presentation, which will be a montage of this whole year's series of seminars. Today's subject is the plasma universe. The NASA Science Council selected this topic because it embraced a lot of the sciences that NASA is interested in, especially the crossover between the traditional space sciences and the earth sciences. The figure that you will see on the screen illustrates just how embracing the plasma universe really is. This figure shows plasmas that can occur naturally or can be created in a laboratory. The plasmas are shown as a function of temperature and density. You can see that the disciplines of NASA embrace a universe of plasmas, from the pulsar magnetospheres in the relativistic plasma regime to the classical plasmas, the Earth's magnetosphere, the solar corona, the solar wind, to quantum plasmas like white dwarfs. With us this afternoon are some of the leaders in the field who are responsible for identifying and explaining the rich collection of plasmas, their behaviors, and the processes that underlie these behaviors. They're going to describe how knowledge of these processes operate in all of the regimes that you see here, and how those processes provide us with a quantitative understanding of the complex terrestrial environment, as well as lead us to understand the origins of behaviors in the astrophysical environment. Space plasma phenomena lead to fundamental scientific questions relating to the behavior of plasmas under extreme conditions, under conditions that are very much different than we observe here on Earth. So we investigate these plasmas in the universe to lead us to a broader physical understanding of plasmas in general. And you're going to hear, too, about some of the applications of plasmas. Applications to ground-based communications, protection of instruments in geosynchronous orbit, and the safety of astronauts in orbit. So now I want to introduce the originator of this series, our NASA administrator, Mr. Dan Goldin, who'll make a few remarks on this subject.
Thank you for coming. The series was scheduled during the government shutdown, and it grieved us, but we had to cancel it and give everybody short notice of coming back the second time. So I'd like to thank everyone who has been flexible enough to come. We've discussed a whole variety of scientific subjects, and if you will, this subject could be the glue that ties it together. When we think of space, we think of planets, we think of suns, we think of small bodies, we think of galaxies. But in that, quote, empty space is a not-so-empty space. There are charged particles, there are gases, and there are things that are among the origins of the universe. So this is a very important subject, and it really began with Dr. James Allen, when he discovered those belts around Earth, the radiation belts. And it was just last Thursday that I was out of the Jet Propulsion Lab, and I was talking to the people assembled there, and I was pointing out, as had been pointed out to me by some of the scientists out there, that they have even more intense radiation belts at Jupiter, and they maximize right around Io. So we made that very critical maneuver to go into Jupiter. The magnetic field, I think, is 10 times that at Earth, and there's a copious quantity of charged particles there, so the radiation is very intense. So A, we'd like to understand it, and B, just to send future probes to Jupiter, we better understand it so we could design those probes. So I'm glad that France pointed out that there was a practical aspect and an intellectual aspect. So today I look forward to hearing about the glue. And with that, I will get off and ask our first speaker to come up.
Thanks. So I have the great pleasure now of introducing Dr. James Van Allen. The era of in situ exploration of space plasma began about 1946 using V2 rockets. And Dr. Van Allen's group of graduate students and himself at the University of Iowa was prominent in this venture. In fact, for 2 decades, from 1945 to 1965, this team pushed the boundaries of experimental technology in examining space plasmas. Dr. Van Allen had a very significant role in the International Geophysical Year of 1957-58, and this culminated with the launch of Explorer-1 in January of 1958. On it was a micrometeorite detector and cosmic ray experiment of Dr. Van Allen's group. With that data from this and also from Explorer-3, which was launched just 3 months later, this group put together the picture that we now have of the local space environment. They made the first space science age scientific discovery, and that was of these donut-shaped regions of plasma, of charged particle radiation trapped by the Earth's magnetic field. These belts of radiation now carry, of course, Dr. Van Allen's name. Dr. Van Allen has extended his studies from the Earth to the larger magnetospheres of the outer planets as an experimenter on the Pioneer spacecraft. His strong advocacy was critical for the success of the mission that we saw last week that Mr. Goldin referred to, the Galileo mission. Dr. Van Allen is presently Regent Distinguished Professor of Physics at the University of Iowa. He's a member of the National Academy of Science and past president of the American Geophysical Union. It has awarded him several of its distinguished prizes, including the Fleming Prize and the Bowie Medal. In 1989, he was given a very singular award, the Crawford Prize of the Swedish Academy of Science. This prize, those of you who are familiar with it know that this is a great honor that it is bestowed in the fields for which the Nobel Prize is not awarded. But perhaps I think what Dr. Van Allen would say is that his greatest legacy is in the young people that he inspired and that he trained, and these are the people who are today providing for the United States leadership in space physics. Dr. Van Allen.
Thank you very much. Well, I'd like to say that the warm weather in Washington is a pleasant surprise for me. Now, about 30 years ago, I gave a talk to the IEEE National Conference at the IEEE, the Institute of Electrical and Electronic and Electrical Engineers, and there was one person in the front row who seemed a little restless during my talk, and as soon as I finished, he popped up and said, I listened very carefully to your description of how protons and electrons wander around in the Earth's magnetic field. But doctor, please tell me, what are radiation belts good for? And my reply, I took that to be kind of a flip question, and I gave a correspondingly flip answer, is, well, they help me make a living. And I consider that a very worthy purpose. So today I thought I'd start with you might call the bottom line of my subject by discussing what are some of what I call significant practical applications of space physics, and see if I can get the right button here to start us off. Looks pretty good. All right, now here are some of the things that we really, I think, have a significant role in the area of practical engineering and operational applications of space physics. The first one is one on which I wrote a paper soon after we discovered the radiation belts, having to do with what I call the radiation-safe corridors for human spaceflight. And I'll show a little more detail on that later, but roughly speaking, you must stay below about 300 or 400 kilometers altitude in order to avoid a significant radiation cruise in prolonged flight around the Earth. And of course, you can make a quick pass, as we did with the Apollo missions, with only a few hours exposure safely. but there is a very strictly forbidden region for space flight with anything resembling the present type of spacecraft. On the lower side, of course, is the air drag. So in effect, you're limited to a fairly narrow lamina of the atmosphere, which lies between the altitudes at which air drag is important and the altitudes at which excessive radiation exposure occurs. Also, there are very important radiation effects on solar panels, electronic equipment, optical surfaces, the exposed surfaces on optical equipment in Earth orbit. And these have the form of two major types. One is what we call signal event offsets, in which like a 0 in a digital chain is changed to a 1, or vice versa. And that is equivalent to dialing a long distance number and making an error in one digit. And you end up by contacting someone in Kentucky instead of Florida. Now, the second one has to do with cumulative permanent damage, which is particularly relevant to solar panels and other types of electronic equipment as well. Now, the next point I wanted to mention was the consequences of high-altitude nuclear bomb bursts. And in the mid-1958, we made the first major series of atomic bomb bursts, the so-called Argus tests. And with our little equipment that we made in our lab on Explorer 4, we made the primary observations of the effects of those high-altitude bomb bursts. The biggest one that has ever been conducted, those were about 1.5 kiloton bursts. The biggest ones ever conducted was the starfish, one called Starfish Burst from Johnston Atoll in 1962, and that was a sort of a major geophysical event. So we've sort of calibrated the system so we know what you can expect from that range of nuclear bomb bursts at high altitude, either by an adversary or ones that we do ourselves. Now, there have been some notable examples of major magnetic storms which have produced large-scale outages in electrical power grids. Some of you doubtless remember a few years ago, I don't remember the exact number, like 5 to 7 years ago time frame, there was a major electrical outage in the whole New England area encompassing New York City and major population centers in the Northeast due to a magnetic storm. And we don't pretend to know how to prevent those, but we do know how to, we are working on the possibility of predicting them so that electrical engineers can develop what you might call preventive protocols of what to do in case one is in the offing. It's something analogous to the Hurricane Prediction Center at Miami, which cannot prevent hurricanes but can give a certain warning to people who might be affected. As a corresponding thing in the disruption of radio communications, this has to do with the effects on the ionosphere, and especially at the lower frequencies, but even at the GPS frequency, which is in the L-band, there's also a significant error introduced to the GPS navigational fixes. And as Mr. Goldin just mentioned, it has to do with engineering design of interplanetary and planetary missions. Specific examples are the design of the encounter of Ulysses several years ago, the European spacecraft, and the recent encounter of Galileo. The mission was conditioned on a tolerable radiation dosage to the equipment. And that's based on the surveys we made of the Jupiter's magnetosphere, first of all with Pioneers 10 and 11, then with Voyagers 1 and 2. And Ulysses also contributed to that. And finally, I didn't remember this until last night, I should mention spacecraft charging, which is a plasma physical effect, which can have significant effects on communication satellites by charging up insulated surfaces and breakdowns of insulation. Now, the sun is the big boy in this whole system. And I won't dwell on this slide much to say that of course, the gravitational field of the sun is fundamental to the orbit of the Earth and all the planets. So that's probably the first thing one should mention. Secondly, our electromagnetic radiations ranging from radio all the way through to gamma ray radiations. Each one of these has its special features and special influence on the Earth. And of course, the most important one is obviously the visible, infrared and visible, which keeps the Earth warm and is our major source of life, of course, it supports life on Earth. In addition, and less well known, are these what we call corpuscular radiations, which are distinguished from the electromagnetic ones by the fact that they're composed of particles or corpuscles. The solar wind, which is a plasma hot ionized gas, energetic particles, neutrons, and neutrinos, in sort of descending order of importance in my subject here. Now, the next view graph tries to respond to the question if you sort of meet an old friend on the street and he says, what is space physics? That's what I'm trying to answer here. And it encompasses the vast variety of phenomena resulting from interactions, and I do want to emphasize the word interactions, among the following classes of particles and fields, and sometimes called particles and fields physics. First of all, electrically charged particles, both electrons and ionized atoms, and their interaction with magnetic fields, electric fields, electrical currents, and they produce electrical fields and they produce magnetic currents, so there's a two-way interaction. Electrostatic, a great variety of electrostatic waves occur in ionized gases and electromagnetic waves. And finally, their interactions with dust and solid bodies, which plays a role in planetary magnetospheres, most notably that of Saturn. Now, I have what I call a kind of a hierarchy of charged particles in space physics, and these read from the top down in order of energy and also in the inverse order of density or number density. First, we have what are called galactic cosmic rays. Those are perhaps the most ancient member of this family in a way, and they're single travelers. The average distance between two cosmic rays and as they come in toward the Earth is about 30 meters or more, so they have absolutely no interaction with each other and are, however, influenced by the magnetic field, by magnetic fields especially. They're the so-called anomalous cosmic rays, which are apparently originate within the solar system and become the kind of the low energy end of the spectrum of the galactic cosmic rays. There are radiation belt particles, which in ranking here according to energy come next, which I'll say more about shortly. Solar energetic particles, those having energy far greater than the particles in the solar wind and are sporadic and in the order of MeV energies. Then there are locally accelerated particles, which is probably a pervasive effect throughout the universe, but is under direct observation by various people in the interplanetary medium and at the bow shock of the Earth. Then there are auroral particles, which are the traditional, most famous manifestation of what we now call magnetospheric physics, and plasmas and ionospheres. Now, some of my friends say that plasmas, that 99+% of all the matter in the universe is in the form of plasma. And of course, the obvious conclusion from that is that plasma physics is 99% more important than the sum of all other subjects. The conclusion may be contestable, but the fact, I think, is pretty firm. Now, next, I wanted to give sort of what I call the hierarchy of magnetic fields that corresponds sort of in diminishing order with the one I had for the particles. And in pulsars, we have estimated magnetic fields of the order of 10 to the 12th power Gauss. That's a million Gauss. At the sun, they range in the order of 10 to the 3 Gauss, although the so-called general magnetic field of the sun is more like a few Gauss. These are in sunspots and other active regions. In the case of the planets, the surface magnetic field in the planets is less than or about 1 Gauss. In the interplanetary medium, it's of the order of 10 to the minus 4 Gauss or less. And the interstellar medium is estimated to be about 10 to the minus 6 Gauss. So that leaves an enormous range of magnetic fields. On the previous sheet, the energies range from 10 to the 14th electron volts down to fractions of an electron volt. On this page, they range over a factor of 10 to the 12 down to 10 to the minus 6, 18 orders of magnitude variation. Now, I have a few slides to give a little more substantive detail to these remarks. Dr. Cordova mentioned the fact that we'd explore. This is a very old slide, I may say. This shows the fundamental discovery data from Explorer 1, which we discovered the existence of radiation belts. And there are 3 sets of curves here. This is a plot of the logarithm of the counting rate of our detector as a function of altitude. Now, the left-hand pair of curves was taken over the eastern South America. All 3 curves refer roughly to the geomagnetic equator of the Earth. The left-hand pair of curves was over stations in eastern South America. The central set of curves was over the west coast of the United States, and the right-hand curve was from over Japan, the longitude of Japan and Korea. One of the most important things we first noted here, and is obvious here, is that the radiation belts comes much closer to the Earth over Brazil, or near Brazil. That's the left curve. It begins at about 400 kilometers altitude is when we first encounter it. Over Japan, it's about, I think it's around about 1,200, I think. The difference between those two is 900 kilometers, which is exactly the well-known value for the eccentricity of the magnetic center of the Earth, which is 450 kilometers, and that's been known for many years before. In fact, it was known for many years that there was a so-called South Atlantic anomaly, a sort of a weak spot in the magnetic field. And these results are, graphic confirmation of that. And I just thought I'd show you the so-called South Atlantic anomaly. This is also a very old slide showing that patch off the coast. We called it originally, I think, the Brazilian anomaly. It's now generally called the SAA, or South Atlantic anomaly. And that shows the patch to which is the dangerous region for radiation exposure. And I've drawn in at least two orbits there, the ground trace of two low inclination orbits, one of which misses it altogether, of course, the other cuts right through the center. Those are just exemplary possibilities. And here, that other one is at 500 kilometers. This shows how that region grows as you go up in altitude. And this is the 1,000-kilometer cut showing the hot spot, the reddish spot, and shows again how it becomes more and more difficult to escape. And all of that is very well covered in engineering manuals, which have been models which have been developed by Jim Vetty and his colleagues at Goddard over the years and are standard for engineering purposes. And here shows one of our early results in which we first found that there are two major radiation belts around the Earth. The inner one, which I've just been discussing, and then an outer, much more distant one. And in the center of that inner radiation belt, an astronaut in a shuttle cabin would receive a fatal dose in about 3 days, in a present type of shuttle cabin, about 3 days if orbiting continuously in the equator at the center of that zone. So this is not only dangerous, it is potentially fatal. Here shows how the magnetosphere of the Earth looks on a much more expanded scale, in which now the radiation belts are just in the inner pocket there in the center. This shows the long downstream wake behind the Earth, which we know extends for several million kilometers behind the Earth. And here is a slide, this might be of interest to Dr. Blanford as well. Here I plot the logarithm of the magnetic moment of the planet. As you know, we've investigated all seven of the 8 other planets. In other words, we've investigated a total of 8 now out of the total of 9 known planets, and of a succession of missions. It's been beginning in 1962 with our first mission to Venus. And we now have measured the magnetic moments of all of those bodies, and I plot here the logarithm of the magnetic moment as a function of the logarithm of the angular momentum. Now this is what's sometimes called, with a sort of a sneer, it's called Bode's law of planetary magnetism. And that's intended as kind of an insult to people like me, and I don't mind that at all, but I just like to say that this is an empirical curve. And I plot all the planets on here, and I might say, and I'll also include that box up there for pulsars, which seems to fall in the same general region. So regardless of the sort of the theoretical contempt for this relationship, I like it because it seems to be a very good empirical representation. As a matter of fact, I made a similar curve before Voyager 2 got to either Uranus or Neptune, and I put a predicted value on there. I was fairly generous about it, I might say. I put in plus minus 1 order of magnitude. So didn't 1 order of magnitude on this scale is not terribly conspicuous, I might say. And Uranus and Neptune, came right in the middle of my error bar. I think that's all the slides. Now I have 2 or 3 more view graphs to show. I must have hit the wrong button here. Let me try this one. That's supposed to be a buzzer for something. There we go. I don't know, how do I kill the other one, I wonder. Oh, okay. All right, now here's sort of looking sort of more toward the future. These are slides which are intended to give a kind of a basic orientation on the subject of planetary magnetospheres. And I list here the basic sources of energy. It's really astonishing how difficult it is to answer very simple questions, like where does the energy come from, where do the particles come from, where do they go, very simple things like that. And we're working our way through one at a time through the magnetospheres. The basic sources of energy for planetary magnetospheres are the kinetic energy of the flowing plasma constituting the solar wind, or in case you're outside of the solar system, it would be the stellar wind. Secondly, the rotational energy of the planet. It's pretty tricky to figure out how you can convert or couple that rotational energy into the energization of charged particles, but many good people are working on that and they're making a lot of headway. And then the orbital energy of the satellites. Now, where do the particles come from? These are potential sources of energetic particles. The solar wind itself, solar energetic particles, which I mentioned earlier on, the primary cosmic rays, some of which may get captured into the magnetic field of the planet. There's secondary particles. We know this one is a very important source. Secondary particles from cosmic ray interactions in the planet's ionosphere, atmosphere, rings, and satellites, very important source of the inner radiation belt particle, the penetrating protons. Ionized gas from the planet's ionosphere, and gas sputtered from rings and satellites by particle and proton bombardment, and gas emitted volcanically. The only example we have of that actually is Io at Jupiter, but that's a very important one. That gas inflates the whole magnetosphere of Jupiter. And where do these things go? Okay, they go in various ways. First of all, by radial diffusion. Once you have particles trapped in the magnetic field of a planet, it tries to respond to the question of where they go and what it is you have to look into in order to understand that. That's the spirit of these various sort of lists I'm making here, is what are the things you need to inquire into in order to understand what's going on. And so this is kind of a shopping list, as you might call it. First of all, there's radial diffusion inward to the atmosphere, and where they're lost in the atmosphere, outward to space. There are various varieties of plasma instabilities, and Dr. Kennel here is one of the world's experts on this subject, including pitch angle scattering by so-called Whistler mode waves and ion cyclotron mode waves. There are collisions with satellites and particulate matter in rings. That's very notably important at Saturn, and also at Uranus and Neptune. It's a charge exchange with ambient gas, and there are also gross perturbations of the weak outer magnetic field. Now I see I omitted a couple of slides, and maybe if I can manage to get back to those, I'd like to show, I think, my last two slides, if they aren't lost by now. Just wanted to show one of Jupiter here, if we can, since it's a fairly live subject this week. Yeah, this is a kind of a dramatic view of Jupiter's magnetosphere, our artist's conception, of course, but we do have a lot of really good measurements on which this is based. And Pioneer 10 was the first mission to Jupiter and did a very good job of surveying the charged particle environment. One of the notable things about Jupiter is that because, as we now know, because of the plasma emitted by the volcanoes of Io, there's an enormous amount of plasma which inflates the field. And that outward pressure sort of tends at the weakest point in the field, which is at the equator, tends to distend the field out in a great tongue-shaped region. And in addition to that, there's also centrifugal force on the plasma. The combination of those two gives a great bent, what we call magnetodisk there. And just to remind you, here's the projected orbiting plan for Galileo, which is now underway. So I think that completes. I'm probably over my time and apologize for that. Thank you.
Thank you very much. That's great. Thank you very much, Dr. Van Allen. Our next speaker is Dr. Ian Axford. He is arguably New Zealand's most distinguished living scientist. He's one of those rare people who seems to be everywhere simultaneously. He's in international demand in forming science policy and program direction because of his exceptional contributions to research and administration. This afternoon, he spent some time telling me about his recent attempts to help New Zealand reform the way that it does its science program and the management of the science. And it's really quite different than the way we do it in the United States. Dr. Axford's original training, interestingly, was in aeronautics in Manchester, England. He came to North America and applied the basic concepts of supersonic flows around blunt bodies to the problem of the flow of the solar wind around objects in the solar system, starting with the Earth. He was the first person to speculate that a bow shock would be standing upstream of the Earth, even though there was no known dissipation mechanism for plasma dissipation at that time. Dr. Axford was director of the Max Planck Institut for Aeronomie for more than 2 decades. He has authored more than 250 papers in space physics, cosmic ray propagation, and acceleration. He has been president or vice president of many distinguished scientific societies, past editor of the space physics part of the Journal of Geophysical Research, and has the prestigious honor of being a foreign associate of our National Academy of Science. He's presently engaged, as I mentioned, in reshaping science in New Zealand, and this year was named New Zealand's New Zealander of the Year. Dr. Axford.
Thank you. It's a great pleasure to be here, and especially to follow Dr. Van Allen, with whom I worked many years ago when Voyager was called MJS and when Galileo was called Pioneer Jupiter Orbiter. We've come a long way since then. Let's get on to space. By our standards, space is empty, or almost, and the scales and the times involved are inhuman. If you stand in the right place, with the right perspective, you can see that space is really filled with stuff and dominated by violence. There are very high temperatures quite commonly, and some particles get accelerated to extremely high energies. These are the cosmic rays. The gas is usually ionized, a plasma, and the magnetic field has an important role. Plasma physics is not just a matter for laboratories and the thermonuclear fusion program. It really began in our field, in astrophysics and space physics. In fact, it began, I guess, with the observations of gaseous nebula and the sun's corona, where people didn't understand the spectral lines they saw because they were not used to the temperatures that existed there. The pioneers of space research were concerned with the plasmas which were connected with the polar aurora, with geomagnetic storms. They developed ideas about the solar corpuscular radiation, or the solar wind, the magnetosphere, magnetic field reconnection, and collisionless shocks. As the pioneers, such as Dr. Van Allen, were concerned with just about all of these problems. Alfvén, as a basis for his theories of such phenomena, invented particle drift concepts and the Alfvén waves, for which he got the Nobel Prize. And the first radio scientists after Marconi concerned themselves with the nature of the ionosphere, a plasma, and developed the theory of wave propagation in this plasma, and a Nobel Prize was given to Appleton for this. Our subject exploded, of course, though, with the onset of the space age. This presented us with the Earth's radiation belts, of which you've heard, the magnetosphere and the solar wind by 1960, and has gone on from then to become a major field of physics and astrophysics. You've learned of some of the subsequent development from Professor Van Allen, and you'll hear of more extreme things from Professor Blanford, I'm sure, far beyond the solar system. I want to tell you something about winds, but not everything. Enough, I hope, to give you some idea of the subject and a feeling for its significance and importance generally. Within the solar system, space is dominated by the solar wind. This was first invented to account for the behavior of comet tails, which look as if they're being blown away from the sun wherever they are, like cosmic windsocks at an airport. On the right there, you see some of the most recent results obtained from Ulysses. This is a plot, a radial plot, of solar wind speed against latitude of the spacecraft. And you can see that around the ecliptic plane, the solar wind speed black curve is fairly low, 400 kilometers per second. But in the higher latitude regions, above about 20 degrees, the speed is about 800 kilometers per second, and it has actually lasted like that for years at a time. Because this trajectory took about 4 years, and the high-speed wind, 800 kilometers per second, persists for years and is homogeneous, more or less, during this whole period. It's a fundamental mode of the solar wind, which I think is only just becoming appreciated. I've plotted on top of this a picture of what the sun's magnetic field looks like at this time, and you can see that the high-speed wind is actually coming out of the polar caps of the sun, where we will find that there are polar coronal holes. I've tried to show this on the next view graph here. We were lucky with Ulysses, after inordinate delays, to eventually be launched so that we encountered the sun at sunspot minimum and saw this beautiful picture, which we got because, as you can see on the top there, the solar corona is quite different at sunspot minimum and at sunspot maximum. Sunspot maximum is a mess. We would have had a lot of trouble understanding what we saw, and most of the wind at that time is the slow component. At sunspot maximum, the solar corona is very beautifully ordered. We have very large coronal holes in the top and bottom, that is in the poles, and these emit high-speed wind. You can see this in the next picture from Yoko. This is taken at about the same time, and the black areas on the top and bottom, partly obscured on the north side, are the coronal holes. These coronal holes show very little UV radiation, but in fact as much energy is coming out of those in the form of solar wind as is coming out of radiation in the rest of the place. I forget how many megaton bombs per second, but it's a lot. A remarkable discovery has been made recently by the Spartan mission. They've been measuring the temperature of the ions above these coronal holes. We expected perhaps 1 million degrees, but you can see here 2 cases. The top one, this is a distribution function of Lyman alpha, if you like. It's the proton temperature is determined by the width. The top one corresponds to a temperature of 4 million degrees, and the bottom one to 5.2 million degrees, at distances of 2 to 2.5 solar radii. This is quite remarkable. We had always thought of 1 million degrees, but suddenly we now know that the solar wind blows so fast because it gets so hot. Just as simple as that. Now, I seem to have got my view graphs out of order, but that's not surprising. Let's go on to the next development from this. There are probably winds. Is this the one you want? It's all right. It'll be okay. I'll readjust, recalibrate.
You have Ulysses right behind you.
It's okay. There are probably winds associated with most stars. In the case of the very hot young stars, they're extraordinarily strong, and they may even cause a significant loss of mass to the star, and they extend out into space to huge distances. If you look into this picture of 30 Doradus, it's in the Large Magnetic Cloud, you can see the kind of mess that hot stars make in the medium. You have a mixture here of stellar winds blowing plasma away from that central region where you see all those 100 or so bright young stars concentrated together. Each has an enormous stellar wind. Some of them have blown up and made supernova, and the rest of them are just shining ultraviolet light out into the whole region and causing it basically to tear itself apart. This is a good example of violence from the World Wide Web. Now, in our vicinity around the sun, the interstellar medium is not quite so violent. It's a little warm, but it's still got a neutral component. Can I go back, please, to the previous one? I've lost a... Oh, dear. I've lost a view graph, the one that was on the left. Someone there that could rescue me? Okay, thank you. This is what we see from Ulysses, fairly close to the sun, of the local interstellar medium. It's quite a remarkable thing. It's a little detector designed just to measure neutral atoms coming and hitting at a target. It just points all around the sky and makes a map. And so here's the celestial sphere. Along the middle of the picture is the ecliptic plane with the planets. The sun is a little yellow dot at the left, is the position, and the Earth is a little green dot next to that. Jupiter is the dot to the right in the ecliptic, and it's shining in neutral atoms, which this thing detects. The Milky Way is the loop, you see, and this is mostly ultraviolet, which the thing is sensitive to. But what's most interesting is the big blob in the middle, and that's interstellar neutral helium atoms coming into the sun, into the solar system. These are interesting because they do have an effect on the heliosphere, which we'll talk about next. But before I do that, I would like to just point out the kind of solar wind measurements which are possible today with today's best instruments. These are spectra of the mass and charge distribution of ions in the solar wind. The top is in a high-speed stream, and the bottom is in a low-speed stream. It's a little hard for you to see quickly what's happening here, but both graphs are made with the same intensity for 6 times ionized oxygen. You can see the elements to the up and the charge horizontal. What one finds out from this is that high-speed solar wind comes from relatively cool regions and is normal composition, whereas the low-speed solar wind comes from a hotter plasma and has a rather peculiar composition enhanced in metals. On the left, you see another piece of violence from the World Wide Web, this time the Orion Nebula. I mentioned that the interstellar medium near us is generally rather quiet, but it may not have always have been so. In fact, there's some evidence that a few tens of thousands of years ago, we were hit by a couple of shock waves from supernova. This must happen fairly regularly. But the solar wind does carve out a special domain in interstellar space. We call it the heliosphere. It envelops the entire planetary system. And here on the right are a couple of models which give you a feeling for this. The heliosphere is just, in fact, what you expect from a bullet in a supersonic wind, going back to my early education, as you pointed out. In the middle of the left-hand picture, you see the supersonic solar wind, the green spherical region, but it runs through a shock wave, the solar wind termination shock, and the gas or the solar wind that remains is then just blown back to the right by the interstellar wind. On the right, you see the same picture, but this time it's neutral hydrogen atoms carried along in the wind. You can see that they're also caught up in this shock wave on the outside. They sort of form a wall of neutral hydrogen outside the heliosphere, which has been detected recently by Voyager and also by HST, Hubble Space Telescope, as I'll show you. The distance to that termination shock is about 100 AU. On the left, you can see how we know that. This is a discovery from Dr. Van Allen's group at Iowa. They found these 2 bursts of radio emission, low-frequency radiation emission on Voyager 1 and 2, and decided that they could only be caused by radiation coming from the far part of the heliosphere, the outermost reaches of the heliosphere. And they were able to connect these bursts with a couple of huge shock waves which were emitted by the sun, seen by the Earth, at the Earth and by several spacecraft, and by plotting it outwards, they discovered the edge must be around 100 AU for the termination shock, and maybe 130 AU for the very edge of the heliosphere. A shock, by the way, is an abrupt jump to a hot, high-temperature, dense plasma which propagates supersonically. You're all familiar with the traffic shock, when you see a lot of brake lights spreading backwards into the traffic when a red light goes on. Shocks usually are accompanied by heating of one sort or the other. In the case of space, they're also accompanied by the production of high-energy particles or cosmic rays. We believe that most cosmic rays are somehow produced by shocks in space somewhere. And that shock does seem to produce a special kind of cosmic ray. And if we can find it, we'll see cosmic ray acceleration in situ, we hope. Now, this brief tour of space has shown that from the sun's corona to the galactic, oh, sorry, I've missed a part. Oh, dear. Yes, there is more to this, I'm afraid. Stellar winds and so on, supernova, tend to make huge bubbles. They come together make huge bubbles in interstellar space. And here's what the situation is near the Earth. You might be able to find the Earth down in the lower left corner of that funny shaped volume there. We're sitting in the vicinity of two large bubbles, super bubbles if you like. These are remnants of old supernova. What I've shown here is there's something rather interesting. On the left at the Earth, we see the neutral hydrogen wall from interstellar gas. On the right, in some other place in the bubble, there's another neutral hydrogen wall associated with another star. Linsky from Boulder has discovered using HST that he can see both hydrogen walls and the hydrogen in between. So for the first time, we've discovered the heliosphere of a distant star, which is quite remarkable. These bubbles, though, exist throughout the interstellar space, and they must eventually escape from the galaxy. The gas is very hot, filled with cosmic rays, and in fact, we don't only have a solar wind and a stellar wind, but we have a galactic wind, as I've shown you here. It looks just like the picture I've drawn of the solar wind. But I'm afraid there's more to it than that. Once you start opening your mind to these things, you can't stop. Clusters of galaxies do the same kind of thing. Here's a part of the Virgo cluster, of which we are a distant member. This is the Coma cluster. You can see these little egg-shaped things are galaxies surrounding a big central galaxy. There are hundreds of them in this case. In this case, we're only looking at the middle, and there are several thousand galaxies attached to that one. The clusters are interesting because they're full of very hot gas, 100 million degrees, which I think probably comes from the galaxies as galactic winds. Once it gets out there, it sits around, tries to cool, and if it has a chance, it does. The gas at 100 million degrees, though, cools very slowly, but there's been a discovery in the last few months of gas in the Virgo cluster, our cluster, at only 500,000 degrees. Now, if I can get this last view graph, you might see it. No, it's not the right one. There's been a discovery from EUVE of a cloud of, there it is, of gas surrounding M87, that central galaxy, which has only a temperature of 500,000 degrees. Its cooling time is such that the amount of mass that falls down is 1,000 solar masses per year, of that order, a tremendous amount. What it suggests to us is, in fact, clusters of galaxies have winds as well. The galaxies throw out gas, it's very hot, cosmic rays. It largely wants to flow out of these clusters and to make a supercluster wind, as it were, with a termination shock, probably around the Earth somewhere. But in the middle, the gas also falls inwards onto the largest galaxy there and just makes it grow and grow and grow. So it's eating up, in fact, its companions. So we can go from solar winds right out to supercluster winds if we like. But where do we go next then? This brief tour of space has shown that from the sun's corona to the galactic cluster winds, the physics and the concepts are all pretty well the same. There's much to be learned from the solar system, where we can make very detailed in situ measurements of what's going on. At the other end of the scale, we perhaps can only measure things remotely, and the measurements are less detailed. But on the other hand, the variety and the sheer grandeur of the phenomena is sufficient to be very interesting indeed. Our customer, however, that's the public, might well believe that it doesn't really need to purchase this kind of research, and it has a right to choose. And when even today a Discoverer-class mission, fully costed, with everything in, might cost up towards $250 million, I think our customer must believe that his investment, his and her investment is a good one, that they've got value for money. Well, I think from my point of view, this might be the case for the solar wind anyway. There are a couple of interesting missions to do. The questions about in the solar wind are, where does it come from and where is it going? Where it's going is out into interstellar space. And you see here the proposed mission to look at the outer heliosphere. It's already in place. It's Voyager, the Voyager interstellar medium. These spacecraft will survive until 2020 AD. They'll reach distances of 130 to 150 AU, and they'll almost certainly pass this shock wave and perhaps go into interstellar space within the next years. So that's worth doing, especially since it's there. Another interesting one is to go close to the sun to see where the solar wind comes from. And this has been proposed in terms of the solar probe mission, a close encounter with the sun, which has to be made during a period of sunspot minimum when there's a well-developed polar hole. And I think with such a mission, provided it's cheap and well-instrumented, we can do a lot towards discovering the origin of the solar wind. I won't discuss the right-hand thing at this point, but wrap up by saying that there's still a lot to be done, but it should be done in a measured and balanced and logical way and at minimum cost, so that our public, our customers, really feel that they've got value for money. Thank you.
Thank you, Dr. Axford. Thank you very much, Dr. Axford. Dr. Roger Blanford will now take us out of the solar system, as Dr. Axford began to do with his picture of the quasars, cluster of galaxies, rather. And Dr. Blanford's going to take us to the universe at large and illustrate how what we've learned by studying the local environment of the sun and the planets of the solar system has helped us to understand the more bizarre denizens of the cosmos. Dr. Blanford was born in England, and he did most of his schooling there, culminating in his research at the Institute of Astronomy in Cambridge, England, with Dr. Martin Rees. And then he came to the States and was at the Princeton's Institute of Advanced Study. And then in 1976, he went to Caltech as an assistant professor, and only 3 years later, he became a full professor, and shortly thereafter, the Richard Chase Tolman Professor of Physics. He's been a visiting scientist at many prestigious institutions nationally and abroad. In 1982, he won the Warner Prize of the American Astronomical Society, which is given to outstanding achievements for a young person in astronomy. He's given many distinguished lectures at universities, including the Marker Lecture at Penn State University and the George Darwin Lecture of the Royal Astronomical Society. He is a fellow of the Royal Society. He's produced a legacy that is very broad. He's consistently applied theory to many, many fields in astrophysics, and his contributions, especially to the theory of active galactic nuclei, are enduring. Also significant is the potency of his work on cosmic ray acceleration. Dr. Blanford, welcome.
Thank you very much, Franz, and thank you very much to you and to Administrator Goldin for your invitation to come here and share this podium with my colleague Ian Axford and also Dr. Van Allen, one of my early scientific heroes. I want to tell you a little bit about the plasma universe and this slide. And as you heard, there's a lot of universe out there, and a lot of it is plasma. And from a physicist's point of view, of course, one is looking at the interplay of ions and electrons, and one is very much concerned about the rich variety of collective effects. There's an orchestra, in fact, that has its own conductor. And this is a model for physicists for the types of many-body behavior one sees in nuclear physics and liquids and so on. Now, the advantage of studying plasmas in the cosmos is that one can observe them under very extreme physical conditions, conditions that one can in no way observe on Earth. And these cosmic plasmas provide passive experiments whereby one can test fundamental theories of plasma physics. And so if we go just to see over here on the right-hand view graph, we see the physical conditions, as already mentioned, in laboratory plasmas as typified by tokamaks, and then in three particular cosmic plasma environments that I shall use as illustrations: supernova remnants, pulsar magnetospheres, and jets. And if we move straight on to the supernova remnants, what one can see there are these are the remnants that are left behind from the explosions of massive stars either the metamorphosis of a star into a compact object, a neutron star or a black hole, or alternatively an explosion of an overloaded white dwarf that will leave behind essentially no remnant. Either way, one has an explosion, and this deposits, I can't resist saying, 10 to the 30 kilotons of energy into the interstellar medium, and these explosions provide sites of heavy element production. It's where we come from in some fundamental sense. They provide the dispersal of this gas into the interstellar medium, and they're a major energy source for the interstellar medium. From the point of view of a plasma physicist, one of the major interests of the supernova remnants is that they are believed to be the site of most of the galactic cosmic rays that we see, certainly up to energies of about 10 to the 14 or perhaps even 10 to the 15 electron volts. And perhaps I can show you the one example of a supernova remnant. This is one that was where the explosion was discovered by a famous astronomer, Tycho Brahe, in the 16th century. And if we have a look at that, I think we should, sorry, oh, can we just go back to that one? Sorry. Take that last viewer. Thank you very much. And this was one that, in fact, left no stellar remnant. And what it produces now is an expanding shock front. Now we can go forwards. And this shock front, thank you, we can go forwards now. This, okay, I think if you go forward on the right-hand one, please. Thank you. Sorry, center one. Go forward on the center one. That's right, thank you. Here we can see two versions of this. Actually, they've both been reversed, unfortunately. But one should be reversed and the other should not be. On the right-hand, your right-hand side, you'll see the radio image of that supernova remnant. And on the left-hand side, you can see the image taken from the Rosat Observatory, in fact, the correct orientation. And what I want you just to focus on is the top left-hand corner of this image. And if we now look at it again in the radio waves, unfortunately, that's been reversed too. Never mind, leave it, it's okay. If we look there, all right, you can see a very sharp feature on the outer side. That is the outer shock front of this supernova remnant. And that is where we believe the cosmic rays are accelerated by bouncing particles backwards and forwards across this shock front. And we can get them from very low energies all the way up to energies of about 10 to the 14 or 10 to the 15 electron volts. And this is a process that we can observe happening in a smaller scale inside the solar system, and one that we would like to understand happening in interstellar space. So, the next slide. Thank you very much. So, in terms of understanding the physics of cosmic ray acceleration, there are many challenges to NASA. And in some sense, the general challenge to NASA is to be able to carry out the same sort of diagnostic measurements that we can carry out in the solar system, to carry out those diagnostic measurements out in interstellar or space or beyond. And so what we would like to do is use X-ray observations and radio observations to resolve and understand what is happening to the plasma and the magnetic field in the, at a strong shock front at a caused by a supernova remnant. And one of the things that we observe there is a great big puzzle, is those little lines that you see in the top left-hand corner are in fact the magnetic field direction. They go perpendicular to the shock front. Naive theories say it should go parallel to the shock front. Let us now, so another challenge to NASA is to try to understand the composition of the so-called knee in the cosmic ray spectrum. Another way of putting this is to understand what is the maximum energy to which these supernova remnants are accelerating the cosmic rays that we see. We think it's about 10 to the 14 electron volts or so, and dramatic confirmation, if you like, of this idea has just come from a recent observation by the Japanese ASCA satellite. And what you can see here are two gray belts of X-ray emission from another supernova remnant, the remnant of an explosion that happened in AD 1006. And what one sees here are, if you like, the grey regions, excuse me, are the sites of the emission by the highest energy cosmic rays of about 10 to the 14 electron volts, and the red, the remainder of the X-rays, are those that are just radiated by hot plasma. And seeing these high-energy cosmic rays being accelerated and emitting directly by the shock front, I think provides a nice dramatic confirmation of the theory of particle acceleration in plasmas. And one way that we can advance this further is by understanding not just the electronic component of the cosmic rays at these energies, but the elemental composition of the cosmic rays, how much iron and carbon and oxygen and so on there is. And the way to do this is perhaps typified here by another part of Mash's mission, which is to do space observations from balloon, if you like. And here, sort of symbolized, one hopes to be, there's a real possibility of doing long-duration balloon flights from Antarctica, which would be one way along the road to understanding the composition of cosmic rays at the maximum energies that they can be accelerated by supernova remnants. There's another very important type of physics experiment that one can do, and this is to try and understand the behavior of cosmic plasma by analyzing the thermal component of the X-rays. And here, the key scientific question, that is one that we're trying to answer in all manner of cosmic environments, is how fast are electrons heated by hot ions, because that very much controls their subsequent behavior. We know how to calculate it in one simple case, but we do not have a good understanding of this process. And theoretically, and the only way we are going to understand it is by observations of objects like supernova remnants. Next slide. Have the next. Thank you. Very good. Now, another challenge, or one of the frontiers, if you like, is to understand cosmic rays of the very highest energy. Here's a view graph I like. It's full of acronyms, and I'm not going to tell you what any of them mean, just to get my own back. And but what I want you to look at the top right-hand corner are the very highest energy cosmic rays, and these are ones that have energies as high as 3 times 10 to the 20 electron volts, and they presumably need about 3 times 10 to the 20 volts in some cosmic source to make them. And probably on general grounds this requires a current, if you think about simple electroengineering, about 3 times 10 to the 18 amps, and multiplying those two numbers together give you a characteristic power of 10 to the 39 watts. Now, this is a massive power, as powerful as the most massive quasars, which is telling you something about the sources. But the trouble is, they can't be any further away than relatively close by, a few times further than the Virgo cluster, because otherwise they wouldn't get here. So we have a real puzzle. We've got to do things very efficiently. If you like, faster, better, cheaper is a slogan that applies to the acceleration of the highest energy cosmic rays, as indeed it does to other types of problem. So there are many candidates for these, for the accelerators of these highest energy cosmic rays, and I've listed some of them here. Some of them are really quite exotic. There's a real discovery to be made here, and one way to advance it is, in fact, a ground-based project, the so-called Auger project, which this is not NASA's job to collect these particles, but what I predict will be NASA's role in this business is to find the sites, to find the origin. And I believe that NASA will actually make this discovery at some time in the future, not with a special purpose satellite, but one of the ones that it has on its manifest. And I think that this is the way we'll find out where these highest energy cosmic rays are made. So let me just go on. Now go on to my second example. These are the pulsar magnetospheres. Pulsars, as I'm sure you all know, were a wonderful discovery of radio astronomy. Happened while I was a first-year undergraduate, and I can remember the excitement of the time. It's been good for 2 Nobel Prizes so far. They are identified as spinning magnetized neutron stars, and they have angular frequencies up to about 600 hertz. For the musical amongst you, that's top E flat. They're wonderful timekeepers. We see magnetic fields, as you've just heard, up to 1 billion times that one sees in the laboratory. And they have confirmed the general theory of relativity. They're currently searching, of course, for gravitational radiation, and there's all manner of uses for them as tools, as cosmic probes. They too are batteries, like the pulsars, but they're not good enough for the highest energy cosmic rays. There you see their meager voltages and amperages. And they're also, of course, mostly seen as radio sources. And here the power is very small, just like the radio power of the sun is relatively small, but the temperatures associated with this power are enormous. Prima facie evidence that one is looking at collective effects that are responsible for these, for the radio emission. And the short answer is we do not know the origin, if you like, of the radio emission from pulsars, and we would desperately like to understand that. We have some idea of what is going on. The temperatures are very high, and so we get the plasma that we are looking at is not one of electrons and ions, but almost certainly one of electrons and positrons. And, so far, we have about 8 detections of pulsars seen in the gamma ray part of the spectrum. Just let me show you here. Just have a look. Next view graph, please, I think. Okay, that's great. Here's the gamma ray sky, and pulsars themselves, as well as radiating the radio emission, also radiate gamma rays, and we have seen them, as I say, about 8 times so far, and we would love to see them in many more environments. What we need to know is essentially, I think the next slide actually shows you a gamma ray detection. Here we see from the BATSI gamma ray telescope, one sees, you can see on the bottom frame here, going through the pulse phase of a 0.2 second pulsar, a fifth of a second period pulsar, stacking up the data. One can see gamma rays coming in a periodic manner from different parts of that pulse phase, and you can see it, if you like, binned in the bottom there, just from direct gamma ray observing, just binning up with the pulse period. And if we move on, and the scientific challenge is to understand where these gamma rays come from and where the radio emission come from. And it now looks like the gamma rays come from the outer magnetosphere. This is a simulation done by my colleague Roger Romani, and then that enables us to locate more precisely where the radio emission comes from, which is terribly important in trying to understand the use of pulsars as timekeepers. And they are, I should remind you, as good timekeepers as anything we have on Earth. There's a real competition, if you like, between pulsar observers and people who make trapped ion clocks and so on, trying to understand who can make the better clocks or use the better clocks. And so this is, again, a very useful thing to do. And what is happening in space is that by observing the gamma rays, one can observe, if you like, the particles in the plasma behaving individually, separately, and observing at radio wavelengths, one sees those same particles acting collectively. It is, if you like, the gamma rays use the approach of Studs-Terkel, and the radio astronomers use the approach of the Harris pole. Okay, so let's just go on to the challenges. That's the next, there we go. The positron-electron plasma physics. We'd love to understand these exotic relativistic plasmas, and what we need is to have more examples and greater resolution on the ones we do have, and that way you will be able to locate the sites of emission, understand the emission mechanism, and in some sense understand the electrical engineering of this spinning magnetized neutron star. And it has many puzzles that we actually cannot solve at the moment on the basis of present data. Let's just go on. Okay, now I want to go to my third example, which are the jets associated with active galactic nuclei. I too am going to show you M87, and here we see a giant galaxy. This is somewhat coincidental, a giant galaxy in the Virgo cluster, relatively close by to us, and what one sees here is on the right-hand panel a jet of emission observed here in the optical, in fact, and one sees this is not in fact the best image of this, but this is a nice long jet that squirts out of the nucleus of the galaxy, at the very center of the galaxy. This phenomenon, seeing jets squirting out of the centers of things, is very common. We know probably 1,000 examples of this. It's a trick that is performed by protostars. It is performed by active galactic nuclei, and it is performed by compact sources in our galaxies, has also just been discovered. And we see it here in the optical. I haven't bothered to put in a slide showing you it in the radio because it looks almost identical. We also observe it in the X-rays, of course, from space. So again, this is a wonderful discovery, and the question is, what is the origin of this jet? How is it formed? Now, we know quite a lot about this particular object, and what we see here is results of space telescope observations that have revealed a disk of gas that is orbiting in the center, and they have confirmed a long-held suspicion that there is a central mass of a couple of billion solar masses that most of us would identify with a giant black hole. What we can see is, okay, what we think we have here is a jet of fluid that is squirting out of the central region of the galaxy with a speed about the same as almost as fast as that of light. And we actually see the features in that knot there move at speeds comparable with the speed of light. So that always indicates that the escape velocity from the central object is about the same as that from a relativistically deep potential well. That is to say, more evidence that we're looking at a black hole. Now, we can observe this jet out to a long way, but we can also observe, this just shows you the central gas disk, and this is a way of actually measuring the central mass associated with the black hole. Let me just move on now. Okay, this is another radio map made by a scientist at the Space Telescope Science Institute, John Beretta, and this shows you how far in you can trace the radio jet. And one is in fact tracing it in to distances of about 10 to the 15 meters, about 300 times the radius of the black hole. What we want to do is to see in as close as we can to the source of the jet to get the best evidence we can for the trick that nature is able to perform to be able to make these jets, presumably by some sort of hydromagnetic flow. If we can understand the jet formation under these circumstances, then we can probably understand it under a wider variety of circumstances in more distant cosmic objects. And so let me, I think, move on to, this is probably my last graph. So the challenge here is to understand how the jets are made, and I think the way forward again for NASA to do this is undoubtedly through interferometry, initially at infrared wavelengths, but ultimately at optical wavelengths. And this will enable us to see the site of the origin at these higher frequencies in much the same way as we've seen them here at radio frequencies. And I suspect the story will be much different and much more interesting in much the same way as if one looked at the sun, firstly at radio wavelengths, and then just studied it as a radio source, and then subsequently studied it as an optical source. And so what we would like to do is to repeat this observation, if you like, at optical and infrared wavelengths, and that would give us the other side of the picture and would perhaps, I hope, let us understand what is the mechanism for the origin of these jets that are quite general. Now, let me just finish. Okay, if I just try and wrap up at this point and say what are the messages that I at least draw from these three examples of space plasmas beyond the solar system. The first is, if you like, an operational one, and that is what is happening, I think in a way that people never really quite suspected would happen, is that space-based observations and ground-based observations are turning out to be remarkably complementary. One does one type of observation in space and then compares it with the counterpart taken from the ground, and the two together give you the big picture. And that is turning out in so many examples to be what actually happens. The second is where I perhaps began by emphasizing, is that astrophysical plasmas exist under conditions unattainable on Earth. We have cosmic laboratories that enable us to understand basic physics in ways that we could never perform such experiments in our own laboratories. And this way we can test fundamental plasma theory. The way forward in many ways for NASA is if it tries to achieve this goal of obtaining the same sort of diagnostics that we have for space plasmas, is of course just pushing on the boundaries of resolution, spectroscopy and sensitivity, and the discovery space is not at all explored. I think as a theorist I can admit in public that the universe has been so much more ingenious and so much more imaginative than we have been, and most of what we have discovered has basically been the unexpected. I cannot believe that it will stop at this stage, and I think that the voyage of discovery in terms of cosmic plasma physics will continue. Thank you very much indeed.
Thank you very much, Roger. Take a seat over here. I'd like to at this time invite Mr. Goldin and our other speakers, Drs. Van Allen and Axford, to join Roger Blanford and myself up on the stage. This is the time when after the talks, when we open this discussion up to our audience and we invite you all to participate and to ask questions of any sort that is on your mind about this subject or its broader applications. We'll start off just by maybe having a few remarks among the speakers, a couple of questions of each other, and then if you'll line up at either one of the microphones, and I'll call on you when I see you standing there. Thanks. Mr. Goldin, would you like to start?
Yes.
Question?
We've been trying to develop a overarching vision for NASA that integrates the fields we had. For many years we've had these separate fields of endeavor, and especially from the speech that Dr. Blanford had, it looks like there's a real coming together of the type of facilities we ought to be putting up, because NASA's about facilities, and then the scientists use those facilities, and we're trying to make our facilities more universal in nature. We're looking at origins as a theme to understand the origins of galaxies and solar systems, origins of planets, and to understand the conditions under which life could exist or form. He talked a lot about measurements in the infrared and optical. We have a very vigorous plan going forward in optical and infrared. We don't have as clear a vision of where we should go in the high energy measurements. Could you make some comments about that, where you think we ought to go? Because beyond AXAP, we don't have real planning, and beyond a few of the other observatories we have up there, we don't have any planning. What would you like to see?
I'd like to see you go to harder X-ray energies. AXAP, as you know, is a soft X-ray mission. I think that to do imaging and, to some extent, spectroscopy in the band above, say, 5 keV, and as far as you can go, is a wonderful opportunity. As you know, if we go up to the highest energies, the egret detector on board BATSI gave you observations from 100 MeV to about 10 GeV, and made wonderful discovery of the gamma ray counterparts of the jet that I showed in M87, the so-called gamma ray jets, and has found about 30 or 40 of those. And has also told us much of interest about gamma ray bursts and other types of cosmic objects and pulsars as well. And I think that the technological capability exists to do much better and find so many more sources, just as one is, if you like, to recapitulate the growth of X-ray astronomy. Looking at the lower energy region between, say, 10 keV and maybe 10 MeV, again, there are the instruments on, the other instruments on BATSI have led the way, and I think that is a frontier that will just be opened up in much the same way as one now has thousands of X-ray sources, where once one only had half a dozen. And I think that that is, you're bound to make discoveries there.
Let me just follow up with one other question. We're looking at interferometry to get really high spatial resolution in the infrared. Mm-hmm. Do you see a real need for very high spatial resolution in X-rays, and would you ever conceive that we ought to put up an X-ray interferometer?
Gosh, that would be wonderful, but quite a challenge, I imagine.
That's what we're about. Let me back off.
Yes, obviously it would be of some interest, but I think that seems to me a less pressing need than others that one has that are sitting there. Yes.
Okay. Charlie?
Would you like to ask a question,
Patiently
Charlie?
waiting.
I didn't expect to be called on so quickly, but I'll ask, I have a couple of questions here for, I guess, everybody. And so I'd like my chance too. And what I'm going to focus on at this point is the issue of continued study of the heliosphere and solar system plasmas in general, and its interconnection intellectually with the astrophysical universe. So I guess I'd like to ask whoever would care to answer, if you could have just one more measurement from the solar system, or an achievement from solar system plasma physics that would illuminate the cosmos beyond, what would you like to see from the program in the near future, or in the future?
I think that's right.
You go first.
We'll pass that on here.
Sounds like being offered your last meal.
Yeah.
You've got one more.
Or your last wish. I wish for 3 more. I think I find it difficult to choose between the origin of the solar wind, the possibility that we may see cosmic ray acceleration at the termination shock of the solar wind, and solving this interminable problem of magnetic reconnection, which you know about, perhaps in the Earth's magnetosphere. But that's a rather universal problem. But I would like 3, if I may, Charlie.
If I try and answer your question literally, I want to get out into the interstellar medium. I want to go through the bow shock.
Okay, so now we have, I think that's clarified an issue. And the next issue that I'm going to be, Van, do you have a?
Yes.
Yeah. Do you have,
Well, I'm very fond of the solar system, I might say, and I'm also very interested in keeping, of course, the 2 Voyagers operating, keeping Pioneer 10 operating, so we make the best conceivable effort with the present spacecraft to actually find and penetrate the termination shock in the heliosphere. That is a reasonable prospect, but not by any means certain during the lifetime of these 3 missions. Otherwise, of course, Cassini is my favorite sort of more or less future mission. And I understand there's an active consideration now for an orbiter of Uranus. And I'd love to get some of these questions I outlined earlier on sort of settled one by one. We have these magnificent magnetospheric laboratories, and every one of them is a challenge, and every one of them is different. Of course, the magnetosphere of Jupiter is one of the grandest phenomena of the solar system, and we're up to that, working on that, of course, with Galileo at the present time. I understand. I think that's everything's going well as far as I know. And I'd like to see corresponding missions. Cassini, of course, is intended to do a similar type of investigation at Saturn, and Uranus and Neptune are very exotic magnetospheres, quite different than the Earth. And so my vision is sort of myopic compared to my colleagues here, but I'm very fond of the Earth and the solar system.
well, I think we now have 3 volts for the Heliopause mission, which I would characterize as slow, unique, but very cheap. And so I would go on for that. Now I'd like to return to, maybe pick up this thread a little bit, Van. You're fond of the Earth. And this is, I think, a question devoted there. I think if you look at the subject of Earth magnetospheric physics and sort of close by heliospheric physics, that we can look forward to a few years of prosperity from the International Solar Terrestrial Physics Program. And I think there will be a number of discoveries that come from that. But I'm also mindful of the fact that this program is a result of 15 or so years of planning. And so it's not too soon to start thinking about what might happen next in this particular field of science, which is, after all, the oldest one And there is the question, should we continue on in a vigorous way in this field? And the planning, I think, will answer that question. But as I look forward, I begin to see a conflict arising in the future planning for this subject. I think there are those people who would like to study less and less with more and more, that want to look more and more at the fine structures of the details within the magnetosphere. And at the same time, I also see the possibility, particularly with the faster, better, cheaper techniques and some of the industrial developments that are occurring, that it may also be possible to study more and more with less and less, and send out, actually, as one of our colleagues, Carl McElwain, speculated, 1,000 spacecraft to do this sort of work. The communications companies are making plans like that now. So the question is, which direction would you go, or how would you balance things out? And finally, can we answer Ian's question, which is, how do you assure the public that you get value for money and interest for money when you do this? So, not that I didn't ask a hard question.
That was a mouthful, Charlie. But very well stated.
Well, I'm not sure that we should be starting to think about what to do next, because there's a very large fleet of spacecraft being launched and about to be launched. Maybe we should see what happens before we start to think about what's going to be done next, and not rush into it too quickly.
Yeah, my concern with that is that it did take us such a long time to plan ISTP, and I'm just a little concerned about the absence of thinking.
Yes.
Could I phrase Charlie's question a little differently? And I'll give you an analog of how we've done it in the field of origins of galaxies and stars and solar systems. We laid before us a 25-year question and said, conceptually, 25 years from now, what questions would we like to answer? Knowing where we want to be, and as one example is, if it exists, we would like to be able to take a picture of a planet within 50 to 100 light years of Earth with enough accuracy to see oceans, continents, and clouds if they exist. Well, at least you know where you are technically. And, well, that's, we're talking about 100 kilometers at, 50 light years. So you say, okay, I got to begin. So we work ourselves back, and we have a modest program which says, in 5 years, we'd like to take a picture of a terrestrial-sized planet, or 5 or 10 years with 1 astronomical unit resolution, to at least get a direct sense that we could see a terrestrial-sized planet. But at least we have a roadmap, and we know where we're going. The concern that I have in relation to Charlie's question is most in the public, because it's not visual. They could understand that picture I just stated, and we could fill in the physics behind it. Space physics is squiggles and lines. And it's not clearly understood by the public. That has a tremendous need to understand and to know. And I guess the thrust of Charlie's question is, could you formulate some basic questions that could be commonly understood by the general public about what questions would we like to answer within the next 25 years? And if you know what kind of questions you want to answer, you could then work yourself back and have a technological roadmap and begin to integrate the experiment. Was that the thrust, Charlie?
That's a good way of saying it.
Yeah. I mean, I gave you 2 or 3 questions that I think are well posed, easily described questions. The origin of cosmic rays, particularly at the very highest energies. I see that as a bona fide, serious scientific problem where there are a lot of opportunities for the answer, and one where one can use space observations to help. The nature of the gamma ray bursts, that of course has been one that has been around now in a quite different form over the last 3 or 4 years, thanks to the BATSI experiment, which has been a wonderful scientific puzzle, and we would love to be able to understand that. The nature of the flow of gas around black holes, or put more pregnantly, how are jets made in a wide variety of environments, many of which involve black holes. That's an engineering trick. We do not know how nature does it. It's like somebody else being able, your competitor being able to do something and we can't. Those are perhaps three of them. I think in terms of communicating this to the public, I think we all have a lot to learn about the means of communication, and I think NASA has made great advances in this. Obviously, visual images are more appealing than spectra, and we have to emphasize the visual. But I think one of the areas where we perhaps don't emphasize as much as we might is the actual technology, the actual trials and tribulations of getting an experiment or a mission to work. And I think that there's a human component to that, and an understanding of the difficulties we were talking about at lunchtime, getting the Galileo probe exactly at the right angle into the Jovian atmosphere. I mean, that is something that, again, I think is communicable and of some considerable appeal, and would be something that I think people would have a real respect for those who manage to pull off this trick.
Roger's three wishes on his wish list directly address Charlie's question about what you could plan for the future and avoid your concerns, Ian, because there aren't any missions. This whole constellation of a dozen or more missions does not address any of those questions.
It's difficult because this is a mature subject in space research now. We have been doing it since Blanford found the radiation belts in 1958, so it's almost 40 years. And it's natural, since the work has been done in a very well, very skillful.
It's sort of myopic compared to my colleagues here, but I'm very fond of the Earth and the solar system.
Well, I think we now have 3 volts for the heliopause mission, which I would characterize as slow, unique, but very cheap. and so I would go on for that. Now I'd like to return to maybe pick up this thread a little bit, Van. You're fond of the Earth, and this is, I think, a question devoted there. I think if you look at the subject of Earth magnetospheric physics and sort of close by heliospheric physics, that we can look forward to a few years of prosperity from the International Solar Terrestrial Physics Program. And I think there will be a number of discoveries that come from that. But I'm also mindful of the fact that this program is a result of 15 or so years of planning. And so it's not too soon to start thinking about what might happen next in this particular field of science, which is, after all, the oldest one. And there is the question, should we continue on in a vigorous way in this field? And the planning, I think, will answer that question. But as I look forward, I begin to see a conflict arising in the future planning for this subject. I think there are those people who would like to study less and less with more and more, that want to look more and more at the fine structures of the details within the magnetosphere. And at the same time, I also see the possibility, particularly with the faster, better, cheaper techniques and some of the industrial developments that are occurring, that it may also be possible to study more and more with less and less, and send out, actually, as one of our colleagues, Carl McElwain, speculated, 1,000 spacecraft to do this sort of work. The communications companies are making plans like that now. So the question is, which direction would you go, or how would you balance things out? And finally, can we answer Ian's question, which is, how do you assure the public that you get value for money and interest for money when you do this? So, not that I didn't ask a hard question.
That was a mouthful, Charlie. But very well stated.
Well, I'm not sure that we should be starting to think about what to do next, because there's a very large fleet of spacecraft being launched and about to be launched. Maybe we should see what happens before we start to think about what's going to be done next, and not rush into it too quickly.
Yeah, my concern with that is that it did take us such a long time to plan ISTP, and I'm just a little concerned about the absence of thinking.
Yes.
Could I phrase Charlie's question a little differently? And I'll give you an analog of how we've done it in the field of origins of galaxies and stars and solar systems. laid before us a 25-year question and said, conceptually, 25 years from now, what questions would we like to answer? Knowing where we want to be, and as one example is, if it exists, we would like to be able to take a picture of a planet within 50 to 100 light years of Earth with enough accuracy to see oceans, continents, and clouds if they exist. Well, at least you know where you are technically. And, well, that's, you know, we're talking about 100 kilometers at, you know, 50 light years. So you say, okay, I got to begin. So we work ourselves back, and we have a modest program which says, in 5 years, we'd like to take a picture of a terrestrial-sized planet, or 5 or 10 years with 1 astronomical unit resolution, to at least get a direct sense that we could see a terrestrial-sized planet. But at least we have a roadmap, and we know where we're going. The concern that I have in relation to Charlie's question is most in the public, because it's not visual. They could understand that picture I just stated, and we could fill in the physics behind it. Space physics is squiggles and lines, and it's not clearly understood by the public. That has a tremendous need to understand and to know. And I guess the thrust of Charlie's question is, could you formulate some basic questions that could be commonly understood by the general public about what questions would we like to answer within the next 25 years? And if you know what kind of questions you want to answer, you could then work yourself back and have a technological roadmap and begin to integrate the experiment. Was that the thrust, Charlie?
That's a good way of saying it.
Yeah. I mean, I gave you 2 or 3 questions that I think are well posed, easily described questions. The origin of cosmic rays, particularly at the very highest energies. I see that as a bona fide, serious scientific problem where there are a lot of opportunities for the answer, and one where one can use space observations to help. The nature of the gamma ray bursts, that of course has been one that has been around now in a quite different form over the last 3 or 4 years, thanks to the BATSI experiment, which has been a wonderful scientific puzzle, and we would love to be able to understand that. The nature of the flow of gas around black holes, or put more pregnantly, how are jets made in a wide variety of environments, many of which involve black holes. That's an engineering trick. We do not know how nature does it. It's like somebody else being able, your competitor being able to do something and we can't. Those are perhaps 3 of them. I think in terms of communicating this to the public, I think we all have a lot to learn about the means of communication, and I think NASA has made great advances in this. Obviously, visual images are more appealing than spectra, and we have to emphasize the visual. But I think one of the areas where we perhaps don't emphasize as much as we might is the actual technology, the actual trials and tribulations of getting an experiment or a mission to work. And I think that there's a human component to that, and an understanding of the difficulties we were talking about at lunchtime, getting the Galileo probe exactly at the right angle into the Jovian atmosphere. I mean, that is something that, again, I think is communicable and of some considerable appeal, and would be something that I think people would have a real respect for those who manage to pull off this trick.
Roger's 3 wishes on his wish list directly address Charlie's question about what you could plan for the future and avoid your concerns, Ian, because there aren't any missions. This whole constellation of a dozen or more missions does not address any of those questions.
It's difficult because this is a mature subject in space research now. We have been doing it since Van found the radiation belts in 1958, so it's almost 40 years. And it's natural, since the work has been done in a very well, very skillfully, that it's becoming almost incremental. Now, that doesn't mean to say the science is not good, but it's very hard to get very excited about the next increment. And I think that the community involved in this has to face up to this and find a way of showing the public that it is interesting. And I'm sure they can do it. It's a matter of having the right touch. Perhaps the important thing is to show that this is not an isolated subject, but there is breadth to it, and the ideas are in fact universal.
I have a different kind of a response to Charlie's point there. It seems to me that NASA has a magnificent set of missions, either just recently launched or about to be launched during the next year. And I'm thinking there, of course, of WIND, which already, I believe, working quite well as far as I understand. SOHO as of last week, Cluster in the near future, and of course the ongoing Galileo mission, Cassini on the drawing boards. All these are magnificent missions, and what I'd like to see is a reduction in what you might call the turnaround time. So when we discover something in one of these missions, it's not for our grandsons to do, but we can do it ourselves within 2 or 3 years. And this point that Mr. Goldin repeatedly emphasizes, and I'd like to join in that very heartily, reducing the turnaround time for response to new discoveries. I think that would keep the level of interest and excitement at a much broader base. Now, as you probably know, I've taught solar system astronomy for at least 17 years, and it's an optional course. It's a voluntary course, and nonetheless, 150, 200 students turn up there every year. And I've been a bit baffled myself as to why they're so interested in the solar system astronomy. But they come in and voluntarily. I think that's an indicator of general popular interest in the subject.
Could I word the question a little bit more aggressively? Because this is a problem that I face as administrator and Wes Huntress faces as the person in charge of the space science program. Up until recently, we viewed our programs as separate entities, and there was a given percentage of the budget devoted to space physics, planetary science, earth science, astrophysics, you name it. We are spending a very healthy amount of money on space physics. Now, given that we've had this unbelievable series of launches around the world, and another year or two we'll have all the spacecraft up, and they'll be operating for such a long time, we are getting a reaction from the space physics community, to put it quite bluntly. What have you done for us lately? And how many new missions must we start now to keep the constituency going? This, I think, is the hidden agenda in Charlie's question, and I'm being a little bit more bold than Charlie was. We have a real problem at NASA. The budget is not just flat, uncorrected for inflation. It's coming down. And if we live with the old world approach, and in fact, I've gone, and France has gone to the National Academy and said, we need you to help prioritize not within fields, but among fields. And given that we want to prioritize, and given that we're looking for synergism, we have a very tough problem. And what we're faced with is the space physics community is very unhappy because we don't have a new start on the books for them, whereas we have a multiplicity of new starts in the planetary program, and we are moving very aggressively for a number of very significant new starts in the astrophysical portion of the program. And I think we're dealing with the issues that Dr. Blanford has brought up. But I'm very worried about what to do with the space physics. And one of the thoughts we had was, let's pause. Let's digest all the data. Let's wait 2 or 3 or 4 years and see where we go. Get the technology ready with instruments, get the technology ready with spacecraft, be able to turn around the program, not in 3 years. Ed Stone is now shooting for 1.5 years on the New Millennium program for instrumentation and for spacecraft. So one approach we could take is, let's hold off on new space physics missions, but have a vigorous technology development program for new sensors and platforms that could accommodate those sensors. Maybe one could even think about not having passive measurements to the heliosphere interface, but to blast out with electric propulsion at an unbelievable speed with small probes that just have particle physics measurements on them, and you could really have a more proactive measurement. But this is a real dilemma, and I think, am I getting at the root cause, Charlie?
Yeah, which technological approach should you follow?
Yeah, right.
Yeah.
Well, you're looking at me. Certainly the idea of having solar electric propulsion finally developed really pleases me. This should have been done years ago, and once we get it, I think a new world will open up in terms of the kinds of missions we can have. The remarks about the space physics community, I think, are well taken. With so many spacecraft about to be launched or waiting or already up there, I think a pause makes some sense. However, I think there's already a problem in money for data analysis. There's going to be so much data coming from these spacecraft that it will require quite a considerable effort to handle it. And I think that 5 years concentrated data analysis wouldn't be a bad thing. The problem probably with the community as a whole, not even the space physics community, is that it's now a buyer's market for research, not a seller's market. You're the buyer, and there's less money than there used to be, and you can be much more choosy. The sellers, of course, 20 years ago were more or less being deluged with money. The world has changed around the other way, and we haven't quite used to it yet. I don't think it's your business to keep space physicists in business as such. Your business is to get the best space science you can, of all kinds. And this change in mindset is going to be rather difficult to make work, but it has to be done, I presume, unless there's more money somewhere.
Let's take a couple of questions from our audience, would you, to start?
I'm David Cherry from 21st Century Science and Technology magazine. I have a question for Roger Blanford. You showed a fascinating slide of the shock of the supernova remnant of Tycho Brahe, showing the side that has the shock on it. You pointed out that the magnetic field lines are at right angles to the shock, and the theory says they should be parallel. Now, I'm not asking you what's the answer, but what I do want to ask, how do you approach the question? How do you tackle that anomaly? Or how does anybody tackle it?
I can tell you what I did, and I can tell you it didn't work. I tried to find a magnetohydrodynamic instability that would account for that observation, and I found it, and then I discovered that it would not grow under the circumstances that were believed to be present at that shock front, so I'm still puzzled by it. I think in terms of understanding the phenomenon more, I would like to see more observations of shock fronts in other supernova remnants to see how general it is. So I mean that's so for me, I'm a theorist, so it's a problem in theoretical plasma physics, if you like, but also that one needs to know more about observations. I think the significance of that is that the cosmic ray emitting electrons, that observation is the cosmic ray emitting electrons show a very sharp gradient in their density, and that implies that they're being scattered very efficiently there, which is an integral part of the theory of cosmic ray acceleration. And so in that sense, it tells you that accelerating cosmic rays in that environment is more or less unavoidable. And so that was a very exciting interpretation of that observation.
The scattering of them is unavoidable.
Is unavoidable, yes, because otherwise they wouldn't have such a sharp gradient in their density.
I have another question that I'm not sure who to address it to. About 6 months ago, David Thompson and McLennan and Lanzarote published a paper that argued strongly that there's a coupling between P-wave modes in the sun and waves in the solar wind. And they also had an argument, not as well supported, that that yes, there are G waves in the sun and that they're coupled to waves that they identified in the solar wind. My question is in two parts. Number one, if we had a complete free hand, are there any technologies that we'd want to put up there to specifically refine those findings? But secondly, of necessity, one has to say that this represents a failure of theory because the P waves are not supposed to get beyond the corona, and even if they did, the solar wind is too turbulent to allow them to propagate, but they do. and then the solar wind gets so thin that there aren't enough collisions to keep them going, and yet they keep going. At least I think I'm representing that right. Anyhow, maybe someone would be willing to comment on what's wrong with our theory.
Well, that was a good paper of Lanzarotti's. Are you contesting the validity of the observations? Or
well, I think the paper is wonderful, too.
No, it's a good paper.
Yeah, very good. I think it does show that our theory is wrong.
Well, I can't tell you what is wrong with the theory, but I'm very happy to accept the observations. And I think SOHO is going to address those same issues. Isn't that correct?
I believe so, yes.
Helioseismology and the influence on the flow of the solar wind. So I'm not a theorist, so I'm not. I'm competent to judge the quality of the observations, but not the implications, I would say.
Thank you.
Thank you for your questions. Yes.
This symposium was billed as related to the plasma universe, and you're concerned about, how to interest the public. The public, of course, is interested in cosmology, and Dr. Axford referred to Hannes Alfvén and his pioneering work with plasmas, but we know that, his model of the universe was different than the dominant model that we live under these days. I wonder if there might be some thought of how research might be directed to explore the, the plasma kind of universe that Hannes Alfvén was proposing.
I think Roger.
I'm afraid I'm not a great expert on late Dr. Alfvén's cosmology. He certainly was one of the pioneers of magnetohydrodynamics, and again, in that context, certainly one of my scientific heroes. Don't think there would be a very broad constituency for his particular ideas about cosmology at the moment, because there have been many observations, most, I think, fundamentally that of the cosmic microwave background, which have fit in so nicely with the hot Big Bang and the evolutionary cosmology. And although there are many important puzzles still in cosmology, I think that most scientists now at least accept that as a starting point.
Are there any other questions from the audience? Dan, do you have any questions?
I want to poke around a little bit with some ground-based measurements. And you talked about radio waves. More and more, we're coming to realize at NASA that we have to pay attention to the synergism between ground and space-based measurements. And in fact, the folks in space science are now an investor in the Keck Observatory in Hawaii. How about radio astronomy? This is something that we haven't looked at for a while at NASA. Yes. What do you think we ought to be doing or looking at in the field of radio astronomy? And I open it up to all.
I would think interferometry, space interferometry, long baseline. So you have the chance to have baseline lines of several astronomical units, which is about the best angular resolution will give the best angular resolution you can expect at this time from anything. I think that is a fairly straightforward matter. The Japanese are already starting in the near future with an interferometer.
Yeah.
Sorry.
A baseline of a few AU?
Yes. The Japanese already have a space interferometer going up. And I think that this kind of approach could lead to the best angular resolution one can, of any part of the spectrum you can hope for at this time, and probably is worth following up. It's not such a big deal.
Perhaps I just flesh it out a little bit. There is a mission VSOP, which will, I think, be launched next summer, in which NASA is already a collaborator, and in fact, calls for proposals have already gone out and been answered. It will be followed, we hope, by a Russian mission, Radio Astron, which will have a slightly larger baseline. I think these will be wonderful opportunities because they will give you better angular resolution. But the concern about going to very large angular resolution is if you don't have a large enough aperture, then you may be resolving out all the structure that you can detect. And so it's not just a question of putting a 10-meter dish one AU away. You've got to put a large enough dish at some distance so that you can actually see something with that sensitivity. The other frontier in radio astronomy in space is low-frequency radio astronomy beyond, below the frequency for the ionosphere. And again, I think there are opportunities there for carrying out cheaper missions in space, because obviously it is much easier to make an antenna in space operating at these low frequencies. And I think that there are, of course, many plans on the drawing board for low-frequency arrays in space, and I think that that's a possibility.
Of course, Bernie Burke is highly in favor of a radio interferometric station on the moon. That has a certain appeal, but I have a little trouble swallowing the practicalities of that, actually.
Well, one of the things that we worry about, if one has an overwhelming need for a radio telescope on the moon, we ought to do it. But we shouldn't put a radio telescope on the moon to justify a mission to the moon. And that's where I think we have to be very, very careful.
Yes, I think it's hazy right now.
Could I, did you have a question, Franz?
Well, I just wanted to sort of summarize where I right now where I think we are with respect to your goals. That you expressed some near-term goals, and I think a certain comfort level that we have a lot of interesting missions on the right now and in the future, that we will be reaching those, and you're excited about seeing what those results are. And Dr. Axford, you think that we should be spending a little bit more on data analysis so we can get the most out of these results and then make a plan for where we want to go next, because we don't, as Roger said, we can expect the unexpected, and that may be in the data that we are collecting right at this moment. And Roger, you're looking at, as I understand it, a new kind of parameter regime, the hard X-rays, the gamma rays, doing opening with new kinds of resolution, angular resolution, spectral sensitivity, a whole new way of looking at these phenomena that we have never been able to look at before. Is that kind of the sense of you all right now? Is there?
I like to see the quick turnaround time. I mean, that's the way scientists really
the quick turnaround
really
time
like to work.
I'm sure we can all agree about that.
That's right. If you're a laboratory scientist, this is the way I started off. You know, if you find out something today, tomorrow you investigate it again and see if it's still right or not. And that kind of thing is very difficult in space, has been extraordinarily difficult because of these enormous delay times and turnaround times. I'd like to see us turn around after a new discovery 2 years later or less. We're up there looking into it.
I think that's excellent.
I think I have a little trouble with these ponderous 25-year plans, to tell you the truth. That's not my style of doing science, I think.
Well, for me, this particular seminar has maybe more than any other shown such a breadth of astronomy, you know, the different areas that this field really touches on, that it is difficult to think of just, you know, one big question that all of it can be embraced into. There are just so many areas that it's out in front of that really what is looks to me like it's called for is a diversity of approaches. And in some parts of the field, it's a real good plan with all the missions for the present, and we need to analyze those. And other parts of the field, the parts that you were talking about, Roger, really need some new technology infused right now and get going and try to figure out the answers to some of those questions.
Astronomy is an infinite subject. I think anyone that lies out in a sleeping bag on a mountain in Montana realizes how infinite it is. We will not run out of problems in astronomy, believe me.
Well, that seems a good place to end on. I want to thank you all very much for such wonderful, enlightening talks and for opening up our understanding of this very interesting and complicated field. And I want to thank the audience, too, for their attention. The speakers will be around for a little while, and you can come up and talk with them and ask them some questions you might have been afraid to ask. Okay, thank you.
Thank you.
Thank you so much for coming.
Yes.
This was valuable.